So separation of gravity wave dynamics, Brodsky wave dynamics, and possibly energy transfers. And I'm kind of in my talk trying to move down to the level of single modes and what single modes are contributing to possible energy transfers and violations of the underlying assumptions. So I'll start with a few basic things about optimal balance, sort of filling in some of the background that Ulrich didn't have time to talk about. And yeah, so the main focus of today's talk is looking at shallow water dynamics of the sphere and energy transfers between Brodsky modes and all other, including equatorial modes. Okay, so optimal balance, just the basic picture of what we are trying to do. So the slow manifold is some parameterization where we have isolated a group of variables that are named Q here. These are the slow variables, and then there are other variables. So this is this P group of variables that is formally fast. And a slow manifold should be something where the fast variables are parameterized with this function phi in terms of the slow variables. As we discussed, Sergey made the point very clearly. In general, the partition between fast and slow variables might not be as clear as the one up here. So here's very clear with the epsilon small parameter and kind of the P group of variables that this is a fast thing. And essentially, if you look at the linear dynamics, then all the slow variables sit in the kernel of the overall linear operator. And so this would be the mock-up for kind of F-plane shallow water or F-plane dynamics in general. All right, and in this mock-up, it's kind of easy to see what is the linear slow manifold. So if you are basically deleting out the nonlinear terms, then, the P dynamics is a kind of oscillatory thing. So J shall be a skew operator, and then P equals 0. So formally fast variables equals 0. A linear slow manifold, and for the nonlinear slow manifold, we construct this mapping typically if we do asymptotics as a series in terms of this scale separation parameter epsilon, and then there are ways to all determine what these coefficient functions of the parameterizing maps would be. And of course, this is a tedious process. In simple cases, it can be done, and some of the models we all know are kind of first order or second order instances of this construction, but it's not very practical. All right. So what we are after is a practical way, and OJ has already used that to do the scale separation. And since we can do it exactly on the linear side, so we have the exact spectral subspace decomposition, we are trying to adiabatically move the linear situation. So this graphics is kind of the back plane, is the linear picture where there's an exact orthogonal splitting between subspaces, and on the front plane, this is the nonlinear situation where we have some kind of complicated slow manifold, doesn't even need to be unique, and it's approximately invariant, but not exactly invariant. And what we are trying to do is kind of connect with some trajectory the linear situation with the nonlinear situation, and that gives us kind of a continuous family of slow manifolds. If we're freezing this homotopy at a certain point. And the hope is, and this can be proved in some instances, that the total evolution, so the red line always stays close to this family of slow manifolds, and therefore we have little leakage of energy between the compartments that we are trying to separate. And this is done technically by just putting this ramp function rho in front of the nonlinearities. So this can be done in an existing code without being interfering too much with existing infrastructure. And then the whole thing kind of becomes, in this setting, a boundary value problem where at the linear end, the boundary condition is we are projecting hard onto the slow modes, And possibly at the nonlinear end, we might want to hit a certain base point, or we basically leave the Q parameter free and just construct this to the evolution from the linear end. And then the P variable, so P of t, so that's basically the vertical variable at the nonlinear end would be a point on the slow manifold over the corresponding value of the Q variable. Okay, so this is an exercise that you can read your students in the first class of differential equations, so it's very elementary. And it's one of these typical examples that mathematicians use to explain slow manifolds in very idealized settings. So the system is a two coupled harmonic oscillators, and they're just coupled from the first harmonic oscillator into the second one with some coupling function. Now, the first harmonic oscillator is written in action angle variable, so basically theta is the phase and it's just going around the circle. So theta lives on the circle, and the second kind of harmonic oscillator is written in terms of complex variables. That's the most convenient way to do that. And then we assume that the first oscillator couples into the second one by a coupling function f of theta. And since theta lives on the circle, we can immediately Fourier expand this. So the ramp function at this point, if you want exact slow manifolds, is just 1. So no optimal balance at this point. And then if you make a Fourier series ansatz, also for basically the g function that is parameterized in the slow manifold, then you can basically solve it directly. So you basically plug in the Fourier series for the coupling function, you make a Fourier series ansatz for the g function, and then you solve for the Fourier coefficients of g. So it's just some simple algebra. And what you see is that you get an exact expression except at certain resonance points where you get a zero denominator, but in principle you have an all-order exact representation of the slow manifold. Now this system you can also solve as a with the ramp function to a certain extent, and then the boundary conditions come in. So the boundary conditions for the optimal balance is that at the linear end, namely when the ramp is down, we shouldn't have any fast motion, so P is all going to be 0. And at the nonlinear end, well, we just say that theta of t is basically some angle that we want to hit. That's the setting of optimal balance. And of course, the theta equation being trivial, you can write out exactly as a linear function. And then you stick it in, and then the second equation you can solve with integrating factors, so the way you learn it in differential equations 1. And then you get the first equation there on the right-hand side. Okay, and so far so good. So this actually came out of the referee report that we received for one of the previous papers. And the referee sort of got to that line and said, well, this is not going to work because I cannot do anything, more or less. And then you kind of remember what you should do with these kind of expressions, and more or less to make progress on these type of problems, you should be integrating by parts. So you integrate by parts, and the second line basically shows what happens if you do it once. And what you find after rearranging terms is that what you get from the boundary part of integration by parts actually gives you exactly what you should be hitting, what you already know from the direct calculation to be a slow manifold, and then you get some junk. And this junk, okay, so it is the first derivative of the ramp function, and then you keep integrating by parts. And that's the explanation to the effect that Ocean was saying, so that you want higher order accuracy in terms of ramp time. So each time you integrate by parts, you pick up 1 over capital T, that's the ramp time. So the more you integrate by parts, the more powers of T you pick up, the smaller the junk term becomes. But you have this whole sort of series of boundary terms that you get, and they better vanish, otherwise you cannot iterate to higher orders. And then if you can basically guarantee that up to order n all the derivatives at the boundary of the red function vanish, then all the boundary terms go away, and you can kind of get any algebraic order you like, and then if you want exponential estimates, it's a little bit more work. That's the basic idea why it works, and it works in much more complicated settings. And yeah, so there's a big history, and I should basically mention that most of what we are talking about has been discovered and rediscovered many times. So the concept of adiabatic invariance actually goes back to early days of quantum mechanics, Born and Fock, and then Kato did the first kind of rigorous theory of adiabatic invariance in a linear operator setting, as quantum mechanics is usually said. Similar ideas come in geometric mechanics, Hamiltonian mechanics context. In fluid dynamics, the idea was first, and I think, to my understanding, completely independently rediscovered by Leibniz and Ritschl in a Lagrangian setting, and they termed it optimal potential vorticity balance because they needed a PV-based solver for the fluid system. And then Colin Cotter realized that there's a connection between Hamiltonian theories, classical stuff, and optimal balance. So he was still working on infinite timeline. And yeah, so Silvano, Manita, and Carsten basically made it more practical by doing time averaging. And so there's a long list of collaborators also on of results that I'm kind of mentioning here today. Okay, so theorems in finite dimension, I just want to mention without actually explaining everything. But in an idealized setting, one can essentially show that the difference, so if you look only at the estimates and nothing else, so P of T is essentially what the numerical optimal balance solver is going to give, and this phi of Q star is what in theory you could achieve if you were patient enough and do an optimal truncation of an asymptotic series to high order. And of course, the order depends on epsilon. So that is kind of swept under the rug. So basically, what the numerical optimal balance solver is doing relative to the best achievable asymptotic result is has this negative exponential dependence on the scale separation parameter. And here, really, epsilon is something like a Rossby number, so it works on the S plane in the geophysical fluid dynamics setting. But for example, in an operatorial setting, is already out of the window. So most of what I want to talk about today is sort of going beyond this setting, and I'm going to skip this. Also, this is sort of Leibniz and Ritschl's original implementation. But skip this as well and just explain very briefly how this works for rotating Shellerwater equations here in a simple setting, and it's essentially exactly in the same way like it works for the mock-up system. So you put the rand in front of nonlinear terms, and then for the linear terms you have to implement the projector onto the different groups of waves. Okay. And so let's move to the sphere, because that's really the interesting stuff to talk about. So these are the Stern relations. So I think Sergey had them up yesterday already. This is about 10 kilometers equivalent depth, shallow water. And what you see is that the Rossby waves, which on the F plane have zero frequency, so they are stationary, start moving, and then there are basically two branches. Of course, all the dots are just the discrete modes that you have. Everything is discrete on the sphere. but they can be organized to these branches, and the violet branch, so these are the viscosity, gravity, or ENI waves. They kind of connect the velocities to the gravity waves, and then we have the Kelvin branch, and we rotate the Earth a little faster, or if you were to reduce the equivalent depth equivalently, then you see that more modes are kind of moving into this gray area. The faster we rotate, the more kind of more we approach a continuum in the spectrum here. And of course, that is poison for organized theory that people have been developing. But we could still ask when everything is discrete here and at sort of standard parameter setting, there are not actually too many modes in this gray area. Can we say something more directly using this method of optimal balance, how these modes in the gray area might enhance transfer of energy, so diabatic leakage, as we say, from the Rossby compartment to the gravity compartment. And the tool that we are using goes back to Sergey and Dieta Zagan. That's this Tiger model that actually solves the rotating shallow watering values on the sphere in terms of the normal modes of the linear operator, the half harmonics. Okay, so we just have some expansion and some notation. And the advantage is that on the one hand, through exponential time integration, so the linear operator is diagonal in the chosen basis, so one can do cheap exponential time integration, and therefore there's no time step limitation due to fast gravity waves. That's kind of convenient. And moreover, in preparing the data and also analyzing the data, we basically have everything fully explicit already, so that makes it the ideal kind of model to study what we are interested in the sphere. All right, and we used the double ramp setup that Ulrich introduced yesterday, so I'm just repeating what he said. So we have this ramp function here that first ramps us up from 0 to sort of the state where we want to study nonlinear interactions. And at the linear end, so when the ramp is down, we can just prepare our fields in whatever way we want to do it. And then in the middle part of the ramp, when the ramp is constant, we have some period of full nonlinear interactions, and we can sort of that's will be typically longer than the ramp period because we are really interested in the undisturbed nonlinear evolution. And then the ramp down at the end basically gets us back into the linear setting, and we have the projection onto the different modes and can analyze the leakage into these various named compartments. Okay, and so this is one of the outputs of my recent PhD student, Mark Empfer. And he was diagnosing diabatic leakage from the situation that was initially prepared in the Rossby wave compartment, then ramped up to the nonlinear state and interact there. And then we see what ends up in the gravity waves. And there are basically 4 scenarios because in the Tyler model, one can, since it's a spectral model, one can switch off certain nonlinear interactions. And so we can switch off the Kelvin branch in the dynamical code or the viscosity gravity and I branch in the code. So these are the blue and the red dots, so we can switch them both. And this is the sort of olive stance. So that's both of them switched off, and then we can see who has an influence on the leakage to gravity waves. And we studied this as a function of the velocity number epsilon. So roughly epsilon equals 1/10 is around the typical conditions, shallow water on the Earth, and then you have sort of a factor of 2 and rotation rate both ways. And that's kind of a factor of 4. velocity number. That's kind of what target can do stably. All right, and what we see is that initially, so for relatively large velocity numbers, we have kind of nice scaling behavior. With the full model, it's a little bit shallower than when we switch off equatorial waves. But then for small velocity numbers, so if we rotate faster than we should, then these two branches diverge, and we see that without equatorial waves, we pretty much have the F-plane scaling that is also expected by theory. That should be exactly 4 by theory. So that matches pretty well. And if we have equatorial Kelvin waves, and only those seem to matter here, then at some point the diabatic leakage actually starts increasing again. So we complete scaling. So here the conclusion is that it's actually Kelvin waves that make the difference. And so we look at specifically now the leakage into Kelvin waves, and that illustrates kind of nicely why we do this diagram setup. So we have 100 hours of simulation, and the up ramp is the first 20 hours, the down ramp is the last 20 hours, and yeah, so the intermediate interaction time is over there. So what you see, if you compare only in the velocity wave compartment, well, of course, all the kelvins are initially 0, and then they start going up. So the red line is the sum of energy in all the kelvins, and then you see the lowest numbered Kelvin volts. And the one that is going up fastest is actually Kelvin volt K equals 2, but at the end of the ramp, it's basically down to practically 0 again. And so the conclusion is that the K equals 2 mode is mainly slaved. So it's part of the slow manifold, of the approximate slow manifold. So if we are going back and assuming that there's little diabatic leakage, then the entire K equals 2 evolution is basically slaved evolution here. The one that persists in the end, and this is for a relatively high rotation rate, that's the K equals 1. So all the diabatic leakage into the Kelvin modes is essentially only in the lowest wave number Kelvin mode here. And you see all the others at the end of the ramp, they are negligible. So all is obviously smaller than the K equals 1 contribution. So we interpret this as this is the true diabatic leakage due to nonlinear interactions between fast and slow, and everything else is practically slow. Okay, so to investigate this a little bit more, we might want to go to weakly nonlinear analysis. So that's kind of writing the shallow water equations in some abstract framework with linear contribution, bilinear form that represents the nonlinear interactions. We can write this in variations in constant form. And then we do a typical weakly nonlinear ansatz. So we say, well, we have basically all the epsilon amplitudes here, and make the ansatz that to first order, we are essentially following the linear dynamics. So we have these rotating waves, and then we have some unknown function at order epsilon squared, and then jump at order epsilon cubed, which we ignore. And sticking this in, it basically works out that so the ansatz simply is correct at the linear order. And the first interesting one is what happens at order epsilon squared, and then we can actually solve for y, and we get some more complicated expression that comes from the fact that in this expression you only have the exact plane waves in the weakly nonlinear approximation, so the exponentials can be integrated out explicitly, and that's this part, and then there are the spatial structure for vision. So this is the speech sensor. And so this whole thing can be sort of read that mode beta and mode gamma are contributing through this sensory relationship into target mode alpha. This we might want to analyze a little bit more, fix some large interaction time. We have basically all the half frequencies. These things can be computed. It's a little bit complicated, but numerical. And then let's look at some of the target modes. So lower order Kelvin modes are the interesting ones here. And see where they actually come from. And so if we fix the target mode, then we basically have two indices for the source mode. So we can do an SVD and basically look what are the dominant contributions that excite a given target mode. And this is what comes out. So this is basically singular value spectrum for each of the target modes that are selected here. So low order Kelvin modes. And this is a little bit bad in this resolution, but this shows these structure and wave number space, the corresponding singular vectors. The interesting thing here to see is, so this is for standard rotation rate, standard equivalent depth, and then, so the singular values decay, but there's a whole bunch initially where there's a relatively high interaction. But we start rotating faster, then the Kelvin k equals 1 mode really sticks out of all of this soup of singular values. And from the singular vectors, the only thing I'm not sure what to finally make of it, but it's kind of clear that target mode k equals 1 in the singular vectors are kind of semi-concentrated. And if you go to some of, so this is always the dominant singular vector, so that corresponds to this first pair. They usually come in pairs, except for when there's a self-interaction, then you have only one, like target k equals 8, but otherwise it's sort of two pairs. And what you see is in the zonal wave number direction, there's an exact convolution condition. So basically, if you want to go to k equals 0 target, you have, I think, this 5 plus 2. So there's an exact condition. In the meridional direction, it's murky. Right? And it gets less and less localized. That's maybe the most striking observation. I don't really know yet what to make of it. Okay, so this is where we stand. The other thing, things were explained by Ojesh yesterday. So I'm just okay. So current work, what to do if all we can do is time averaging. And then hopefully in the future that we move to 3D models, full open models, possibly, and also more systematic higher order singular value decomposition of this transfer tensor to really see if we can get a low rank representation of what is really happening between the nonlinear poles. All right, so thank you for your attention.